Hi, welcome to the Mutant City. I'm Kathia Esquivel, and this work was done with Dr. Fasad. Okay, let's get started. I'll tell you about the Moran processes. This is a process that develops randomly over time. It can be used to describe how a mutation can spread in a finite population. Let's see an example. Suppose that in a population we have two types of individuals, residents and mutants. Suppose there are 2 residents and 1 mutant. We randomly select an individual, say this one to reproduce, and another individual, say this one to die. This is the probability of having selected each one. The probability of selecting a resident is 3 residents divided between the 4 individuals, and the probability of selecting a mutant is 1 mutant divided between the 4 individuals. The product of these probabilities means the probability of having chosen some mutant to reproduce and some resident to die. We have this new population. Again, we randomly select an individual to reproduce and another to die. The probability of selecting a resident is 2 residents divided between the 4 individuals, and the probability of selecting a mutant is 2 mutants divided between the 4 individuals. And again, the product of these probabilities means the probability of having chosen some mutant to reproduce and some resident to die. We have this new population. Again, randomly select an individual to reproduce and another to die. The probability of selecting a resident is 1 resident divided between the 4 individuals, and the probability of selecting a mutant is 3 mutants divided between the 4 individuals. And again, the product of these probabilities means the probability of having chosen some mutant to reproduce and some resident to die. Now, we have this new population. If I choose a mutant to reproduce and a mutant to die, they are 100% likely to be chosen because all individuals are mutants. So the probability that this happened is 1. But if I want to choose a resident to reproduce and a mutant to die, the probability is 0 because there are no residents. When at some time all individuals are mutants, the mutation is said to be fixed. But if the opposite happened, when at some time all individuals are residents, it's said that the mutation is extinct. This is called states, and this is a states diagram. First, we have the state 0. In this state, all individuals are residents. It has not exit arrow because there isn't a way for a mutant to reproduce. They will always be only resident over time. In state 1, there are 1 mutant and 3 residents. We can choose a resident to reproduce and a mutant to die, and we go to the state 0, or we can choose a mutant to reproduce and another to die, and we remain in the state 1, or we can choose a mutant to reproduce and a resident to die, and we go to the state 2. In the state 2, there are 2 mutants and 2 residents. We can choose a resident to reproduce and a mutant to die, and we go to the state 1, or we can choose a mutant to reproduce and another to die, and we remain in the state 2, or we can choose a mutant to reproduce and a resident to die, and we go to the state 3. In the state 3, there are 3 mutants and 1 resident. Again, we can choose a resident to reproduce and a mutant to die, and we go to the state 2, or we can choose a mutant to reproduce and another to die, and we remain in the state 3, or we can choose a mutant to reproduce and a resident to die, and we go to the state 4. Finally, we have the state 4. In this state, all individuals are mutants. It has not exit arrow because there isn't a way for a resident to reproduce. They will always be only mutants over time. So, what is the probability that the mutation achieves fixation and extinction? Let us call n the total population, k the mutants population, and n minus k the residents population. Then, The probability that it will change to the next state with one more mutant is the probability that a mutant will reproduce, product, the probability that a resident will die. The probability that it will change to the next state with one less mutant is the probability that a resident will reproduce, product, the probability that a mutant will die. And the probability that it will change to the next state with the same number of mutants is 1 minus the previous 2. The diagram of a state looks like this. Here are the mutants, the probability of going to the next state with one less mutant, of staying with the same amount, or of having one more mutant. For the example with 4 individuals, the diagram looks like this. If we substitute the values, K isn't the same because the number of mutants depends on the state we are in. Okay, being in any state, what is the probability of reaching extinction? Without loss of generality, let's see what is the probability of reaching extinction given that we are in the state 2. The probability of reaching extinction given that we are in state 2 is the probability of changing to the state 1 product, the probability of reaching state 0 if it's in the state 1, plus the probability of staying in the state 2 product, the probability of reaching the state 0 if it's in the state 2, plus the probability of changing to the state 3 product, the probability of reaching the state 0 if it's in the state 3. If we make this change using lambda, we have this system of equations. They represent the probability of reaching the state 0. Here we have the probability of reaching extinction of the mutation given that all are residents. It's 1. And the probability of reaching extinction if all are mutants is 0 because there are not residents. So, being in any state, what is the probability of reaching fixation? The procedure is the same, but considering that now we want to get to the fixation. These equations represent the probability of reaching state 4. Here we have the probability of reaching fixation of the mutation given that all are residents. It's 0 because there is no mutation. And the probability of reaching the fixation if all are mutants is 1. Okay, but what if some can reproduce more than others? Suppose that our individuals are now different because they have a different reproduction rate. Let's say the mutant is strong chips. R indicates how big the reproduction rate of the mutants is relative to the reproduction rate of the residents. If R is greater than 1, the mutant is more likely to reproduce. If it's less than 1, it's less likely to occur. And if it's 1, it's called neutral drift. That is the case we have already studied. Following the previous steps but taking into account this reproduction rate, the probability that it will change to the next state with the one more mutant is the probability that a mutant will reproduce, product the probability that a resident will die. The probability that it will change to the next state with one less mutant is the probability that a resident will reproduce, product the probability that a mutant will die. And the probability that it will change to the next state with the same number of mutants is 1 minus the previous 2. The probability that will eventually be reach fixation if we are not in the neutral drift is this. Now, We have already seen what can happen in a population, but what happens geographically? For this, we will use a model with graphs. If we have a map, a plane with continuous regions, for each region we put a vertex. If the regions are neighbors, we place an edge and we have a graph. Remember that there are also the graphs and this can have weight. If the individuals are vertex, they might look like this. Suppose the mutant is randomly chosen to reproduce. Then we are going to randomly choose from among its neighbors the one who is going to die, considering their probability. The temperature of a vertex corresponds to the weight of its in degree. A vertex is hot if it's replaced often, and cold if it's replaced rarely. But if they have the same temperature, we have the isothermal theorem. This theorem ensures that the vertex of a graph have row fixation probability if and only if they all have the same temperature. Let's see an example. This is the Mexico City. We place a vertex for each region, and we place an edge between neighboring regions. If a virus arrives that causes a mutation, most probably it will arrive in this region because there is an airport. These are your neighbors, and we calculate the probability that the next time there will be a more infected region, or will be a less infected region, or that it does not change. The probability that there will be another contagion is greater than the probability that the virus will disappear. So, it's more probably that eventually all of Mexico City will become infected. But if another virus arrives, which is more contagious, suppose this has a reproduction rate of 2. Suppose you arrive at the same place, has the same neighbors. Again, we calculate the probability of each time. We have a 1 mutant, 3 neighbors, 16 vertex, and the rate of 2. The probability of another contagion is much greater than the probability that the virus will disappear. This means that the entire Mexico City is more probably to eventually become infected much faster. Okay, it's important to have a mathematical perspective on how a mutation spread in a population. This gives us tools to know what could happen and how to act. Although it's still necessary to consider other factors in the contagion process. I thank my advisor and my illustrator. Thank you and come back soon to the Mutant City.